So now let's continue to problem 10. So if a0 plus a sub 1 plus a sub 2, etc. plus dot 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 plus an is equal to 0, and we are asked to show that the limit as n approaches infinity of a0 times square root n plus a1 times square root n plus 1 plus a2 times square root n plus 2 plus dot 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 plus ak times a times square root plus square root times n plus k is equal to 0. Yeah, so show that this whole limit is approaches 0, so equals 0. If you don't see how to prove this, try the problem solving strategy of using analogy, and basically try the special cases k equals 1 and k equals 2 first. If you see how to prove the assertion for these cases, then you will probably see how to prove it in general. Alright, so now let's take a look at the solution. Basically, we're given this, and then we have to show this. And we're given a hint to use analogy. So my calculus book describes the problem-solving technique of using analogy as follows. So use analogy. Try to think of an analogous problem, that is a similar problem, a related problem, but one that is easier than the original problem. If you can solve the simpler problem, then it might give you the clues you need to solve the original, more difficult problem. For instance, if a problem involves very large numbers, you could first try a similar problem with smaller numbers. Or if the problem involves three-dimensional geometry, you could look for a similar problem in two-dimensional geometry. Or if the problem you start with is a general one, you could first try a special case. Alright, so we are hinted at trying a specific case. Basically, use analogy to just break it down and or try something simpler as opposed to trying to solve the full problem right away. So let's try the special case of k equals 1 and k equals 2 first. So let's first try the case k equals 1. So for k equals to 1, we have a0, so this goes all the way to k is 1, so we have a0, a1. So a0 plus a1 equals to 0. So a0 plus a1 is equal to 0, and then we gotta show this setup here. And if we could solve this, so then a1, move this over to the other side, so that means a1 is equal to is equal to negative a0, like that. So we could throw this inside. And now we're going to take the limit. So limit as n approaches infinity of a0 times square root n plus a1, let's put it here, plus a1 times square root n plus 1. And let's go back above here. So that is what we're asked. And so then you have a0 square root n, a1, and then n plus 1. In our case, when you have n is 0, actually we haven't got to that, but yeah, it's just square root n and then square root n plus 1. So yeah, that's what we have there. And we know, and we just end up at ak is 1. So we don't, and this is n plus k, yeah. So we go all the way until k is 1. Yeah, so that's k, yeah, so we go to k is 1, so we just stop there. And then again, we have to take the limit as it goes to infinity. So it's a bit more work here. So let's go, so now we have this. And now we're going to take our a1 and throw that inside here. And then, yeah, what we end up having is this equals to limit as n approaches infinity of now it's going to be a0 square root n minus a0 square root n plus 1. Alright, so now that we have that, and we're gonna now factor out the a0, so this equals to a0 times by limit, so limit as n approaches infinity of square root n, let's write this a bit neater, square root n minus square root n plus 1, like that setup. And this is all bracket times it by, yeah, so we just have this, and now the trick is, calculus book does it, is, well, we'll multiply this by, instead of minus, same thing but plus, we'll have a bunch of cancellations. So we're going to multiply this by square root n plus 1, and divide it by square root n plus square root n plus 1, like that. And notice a bunch of cancellations. Notice that we're going to multiply this inside top, and then over here, this goes here, etc. And then this multiplies this and that, etc. So I'm just going to erase that. So this equals 2. So it's equals to a0 times by limit as n approaches infinity. And now we have n times square root n times square root n is equal to, let's put a giant line like this. This just equals to n. And then we have square root n times square root n plus 1. And that is just going to be, I'm just going to keep that out of there. So plus, this is, yeah, again, square root n times square root n plus 1. Square root n times square root n plus 1. Like that. And just because it's not the same base inside there, it's not the same thing that you're square rooting. And then the next one is negative square root n plus 1 times over here. So we're going to subtract it as square root n times it by square root n plus 1. So we're going to cancel these two out. Those cancel. And then the last one, negative square root n plus 1 times this one here. That just becomes, well, the square roots cancel. And we're going to become n plus 1. And yeah, I forgot a minus sign here. So there's a minus here because we have this minus there. And we're multiplying here. So this one, this by this, and this by that. So we'll have a minus over here. And then divide this all out by, well, this part here, square root n plus square root n plus 1. So what this equals to, is, well, this just becomes a0 times it by limit as n approaches infinity. So everything cancels, even this one cancels with this. All we're left with is a negative 1 there. So negative plus 1, so it's going to be negative 1. Negative 1 over square root n plus square root n plus 1, and now we could take the limit because we couldn't do it before because you have a bunch of infinities and etc. You'll have infinity minus infinity and so on. So now we have over here, this becomes, well, at the bottom, yeah, or actually here, just this whole thing. I'll just do this whole thing. This approaches, well, negative 1 over infinity plus infinity. So as n goes to infinity, if square root infinity, it's still going to be infinity. So square infinity or infinity is both approaching negative 1 over infinity. In other words, it's approaching 0. So this equals to 0. So we've proved it for case I. So this limit approaches 0 there. All right. So now let's try the general case. We can actually see that how we can solve this. Although the hint gave us, asked us to try special cases k equals 1 and k equals 2 first. The solution manual doesn't do k equals 2, and I'm not going to either. So I'll just jump straight ahead to the general case. So let's try the general case. So we're given that a0 plus a1, so plus a1 plus a2 plus plus ak is equal to 0. So that is what we're given. Remember, for k equals 1, we just go a equals 0, no, a0 plus a1, etc. But now we have a all the way to ak. So this means, and we're going to do the same thing. So if we had a1 is equal to minus a0, so then k equals n would just be minus everything else. So we have this. And now we're going to move all this over to the other side. So that means AK is equal to negative A0 plus, or negative A0, negative A1, negative A2, minus all the way until negative A, or put the negative sign, negative A K minus 1. So this whole thing equals to this. I'm going to box this out because this is important. I'll box the whole thing out because we're going to be throwing this into the entire limit. All right, so thus we have limit as n approaches infinity of a0 square root n plus then it's going to be a1 square root n plus 1. And yeah, let's just go back to the limit, how it looks like. So yeah, n plus 1 keeps going on and on. So square root n plus 1, square root n plus 2, all the way to n plus k. And we get, yeah, plus a2 square root n plus 2 plus dot 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 plus ak, so ak like this, square root n plus k. Alright, so we have all that. So what it means is, well, we know ak is equal to this. So what we'll do is write this as, well, this equals to, we'll have two parts. So this equals to limit as n approaches infinity of, and then the first part is on the top. I'll just do this bracket like this. a0 square root n plus a1 square root n plus 1 plus a 2 square root n plus 2 plus dot dot dot. Instead of going all the way to ak, we'll go to ak minus 1 and then square root n plus k minus 1. Like that. So we're going to go the second last term, and then we're going to replace ak with this equation. So we're going to have now plus, and I'll put this all over here, plus plus negative, I'll put this all in a giant bracket, negative a0, negative a1, negative a2, negative dot dot dot, all the way to ak minus 1. This is k minus 1, and then we'll have square root n plus k, like this. And this is all closed bracket. And again, this right here, this whole thing is equal to our ak. Like that. And now what we'll do is a pretty cool magic trick. So I'm going to take this this right here, I'm going to factor out the a0 from this and multiply this inside to each one. So we're going to do that to each one. So this equals 2, and then take out the a0. So a0 times by limit as, limit as n approaches infinity of each of these separate stuff. So we're going to take out this a0. This is going to be now square root n, and then minus square root n plus k, like that. And then we're going to do the same thing for this one and multiply this inside this right here and factor that out. So this equals to a1 times the limit as n approaches infinity of, this is going to be n plus 1 and then n plus k. So n plus 1 minus square root n plus k, and then dot dot dot, keeps going on and on. So plus dot 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 plus the last one is, well, this multiplied by this inside here, and we're going to go and factor this out. So this is going to equal to now ak1 or k minus 1 times it by the limit as n approaches infinity of square root n plus k minus 1 minus square root n plus k. And now this is the exact same thing as this setup here, square root n minus square root n plus 1. But instead we're going to be dealing with n plus k minus 1 and then n plus k. And then we're going to multiply the top and bottom by the same thing, by n plus k minus 1 and then times plus n plus k, and then divide it by that. And then we're going to do a bunch of cancellation. We're going to have a similar, or pretty much, very, very similar setup. And it's going to be 1 over infinity approaches 0. So every single one of these is going to go to 0. So, yeah, so we could just put this whole thing equals 0, but Calculus book just has some more writing just to clarify. So each of these limits is 0 by the same type of simplification as in the case k equals 1. So we have put it all together, a limit as n approaches infinity of a0, of a0 times square root n plus a1 square root n plus 1 plus a2 square root n plus 2 plus dot dot dot, just for completeness sake, square root n plus k. This all equals 2, and then this equals to, all this is equal to 0, so then this equals to a0 times 0 plus a1 times 0 plus a2 times 0 plus dot 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 a k minus 1 times 0. So this whole thing is equal to, you guessed it, 0. And we've proven our setup. So there it is. We've proven the question that we're asked to prove. So it says use this to prove that this whole limit equals 0. And we just did.